Reading Euclid can be kind of challenging because the methods of proof, the terminology, is not exactly our modern terminology and our modern methods. So, what I would recommend is that you start from the beginning of the book because you will get used to the terminology and the language that Euclid uses, and also you will see examples of very basic things and how they are proved, and then you'll get into the swing of it. Here's my favorite proof in all of Euclid, Proposition 20 in Book 9, where he proves that there are infinitely many prime numbers. Here's the proof. A few things to notice, first of all, is that the proof is geometric. It's kind of amazing that all of Euclid is about geometry, but this is clearly a proof about numbers, about arithmetic. Second, that Euclid is proving that there exist more prime numbers than any finite quantity. And third, that the proofs are sort of like a kind of an example of the general proof that we would consider today. And in this proof in particular, he's only showing that if there are 3 primes, then there's got to be at least 4. In the proof, Euclid says, okay, let's suppose there are 3 primes A, B, C, and we're going to show that there are more primes than A, B, and C. Let's suppose, for example, that A is 2, B is 3, and C is 5. Then Euclid says, okay, take the smallest number that is measured, which is a multiple of all 3 A, B, and C. So from D to E is that number, which in our example would be 30, and then says, okay, add 1 more unit. So D to F, this length would be 31. Euclid has already shown that any number, in particular from D to F, is measured, is a multiple of some prime. So suppose that D to F is measured, is a multiple of G. Well, then in our case, G has to be 31 because 31 is prime, but it could be some other prime. But if this prime G was one of A, B, and C that we already know, then G would be a divisor of DE, because DE was the smallest number that is a multiple of all A, B, and C, and it would also be a divisor of DF. Then that prime G would divide also the difference of those 2 lengths, because this is divisible by G and this is divisible by G, but their difference is 1. So G would be a divisor of 1, but no prime is a divisor of 1. Therefore, we've reached a contradiction, and G cannot be A, B, or C, so it's a new prime. In our example, what we reached as this DF is divisible by a new prime, and in this case 31 is a new prime other than 2, 3, and 5. And that's the proof.